welcome to this problem walkthrough. Today, we'll explore an interesting challenge from LeetCode, problem number 851 titled Loud and Rich. This problem combines elements of graph traversal and reasoning about constraints. Let's dive in and break it down step by step. The problem Loud and Rich introduces us to a group of people numbered from 0 to n1, where n represents the total number of people. Each person in this group has a certain amount of money and a specific level of loudness. To represent the relationships between these people, we are given an array called richer. In this array, each element is a pair x, y, which means that person x is richer than person y. Importantly, this relationship is transitive. For example, if person x is richer than person y, and person y is richer than person z, it implies that person x is also richer than person z. Additionally, we have an integer array called quiet, where the value at each index represents the quietness of the corresponding person. These values are unique across all individuals. The goal of the problem is to determine, for each person I, the person P who satisfies two conditions. First, P must be no richer than person I, and second, P must have the smallest quietness value among all such people. If multiple people meet these criteria, any valid answer is acceptable. Now let's break down the input and output formats for this problem. The input consists of three main components. First, there is n, an integer representing the total number of people, which is equal to the length of the quiet array. Second, we have the richer array, which is a list of pairs where each pair x, y signifies that person x is richer than person y. Third, we have the quiet array, where the value at index I indicates the quietness of person I. On the output side, we need to construct an integer array called answer. Here, answer, I, will represent the person P who satisfies the two conditions discussed earlier. P must be no richer than person I, and P must have the minimum quietness value among all eligible people. To clarify this further, let's look at an example. If richer is given as 1, 0, 2, 1, 3, 1, and quiet is 1, 0, 3, 2, then the output will be 0, 1, 1, 3. This means that for each person, the corresponding value in the output array represents the quietest person they are not richer than, including themselves. To understand the output better, let's examine the explanation for the previous example. For person 0, there is no one richer than them, so the answer is simply 0. Moving to person 1, we find that they are richer than person 0. Since person 1 has a lower quietness value than person 0, the answer here is 1. For person 2, we must consider both person 2 and person 1, as person 2 is richer than person 1. Among these, person 1 has the lower quietness value, so the answer is 1. Finally, for person 3, there are no individuals richer than them, so the answer is 3. Another example highlights a simpler case. If the richer array is empty and quiet is 0, the output is 0. Here, since there are no richer relationships and only one person, the answer is simply the person themselves. In the simpler example where richer is empty and quiet is 0, the answer is straightforward because there are no richer relationships to consider, and only one person exists. The constraints of the problem provide us with important boundaries to keep in mind while solving it. The number of people, n, can range from 1 to 500. The length of the richer array can vary from 0 to n asterisk, n1/2, ensuring that all relationships are unique. Additionally, the values x and y in richer pairs are always between 0 and n1, and x is never equal to y. The quiet array has a length equal to n, and all its values are unique. These constraints help define the problem space and ensure that our solution is efficient and adheres to the rules. Finally, there are several edge cases to consider. If the richer list is empty, the answer for each person is simply themselves, since no one is richer than anyone else. For a single person, the answer is straightforwardly 0, because there's only one person to consider. In cases where the graph formed by the richer relationships is dense, we need to ensure our solution can handle the increased complexity efficiently. On the other hand, if the graph is disconnected, meaning some people are not connected by any richer relationships, our solution should still correctly evaluate each component independently. Lastly, when multiple paths in the graph lead to the same person, we must ensure that the person with the smallest quietness value is selected, resolving any potential conflicts. These considerations are critical to ensuring that our solution is robust and handles all types of inputs effectively. To approach this problem, we first consider a brute force method. The intuition behind this is straightforward. For each person, we traverse all the richer relationships to find individuals who are wealthier than that person. Once we identify this group, we compare their quiet values to determine the quietest person. However, when analyzing the complexity, we see that this method has a time complexity of n squared, where n is the number of people. This is because, for every individual, we may need to check all others. Additionally, the space complexity is n to store intermediate results. The main drawback of this approach is its inefficiency for large inputs, particularly when n can go up to 500 and the number of richer relationships can reach 10,000. Repeated calculations make this approach computationally expensive and impractical for real-world scenarios with such constraints. To address these limitations, we explore an optimized solution using graph theory. The optimized approach leverages the observation that the richer relationships form a directed acyclic graph, or DAG. By representing these relationships as a graph, we can use depth-first search, or DFS, to propagate the information about the quietest person in an efficient manner. Specifically, we create an adjacency list to model the graph and use an array called answer where each entry represents the quietest person for a given individual. The steps involve performing DFS for each person, traversing their richer connections, and updating the quietest person based on their quiet values. Memoization plays a critical role here, as it allows us to store and reuse results, avoiding redundant computations. In terms of complexity, this approach is much more efficient. The time complexity is n plus e, where n is the number of individuals and e is the number of edges in the graph. The space complexity is also n plus e, accounting for the adjacency list and the answer array. While slightly more complex to implement than brute force, this approach is highly scalable and avoids the inefficiencies of repeated computations. The decision to use a graph-based approach was driven by its ability to handle large-scale inputs effectively. By recognizing that the richer relationships form a DAG, we can utilize graph traversal techniques to propagate information efficiently. Memoization is a key advantage here, as it minimizes redundant work and significantly reduces the overall time complexity. Some key insights that led to this solution include recognizing that the problem can be modeled as a graph, using DFS to traverse the relationships, and leveraging memoization to streamline the process. When comparing trade-offs, the brute force method is easier to implement but lacks scalability, making it unsuitable for larger datasets. On the other hand, the graph-based approach requires pre-processing to build the adjacency list, but its efficiency makes it the clear choice for this problem. Ultimately, this strategy not only meets the constraints of the problem but also ensures optimal performance. The final implementation uses DFS with memoization to achieve the desired results. The Python implementation begins by constructing the graph using a default tick to represent the adjacency list. For each richer relationship, we add an edge to indicate who is wealthier. We then define a DFS function to determine the quietest person for a given node. Within the DFS, we first check if the result for the current person is already computed. If so, we return it immediately. Otherwise, we initialize the quietest person as the node itself and recursively explore its neighbors. For each neighbor, we compare the quiet value of the candidate with the current quietest person and update accordingly. Finally, we iterate through all individuals and perform DFS to populate the answer array. This implementation efficiently handles the problem by leveraging the graph structure and memoization, ensuring that each person's quietest richer counterpart is calculated accurately and in optimal time. To solve this problem, we need to identify the quietest person among all individuals who are at least as rich as a given person. The input provides a list of richer relationships, which specify that one person is wealthier than another. Using this, we must construct an output array where each element represents the quietest person in the group of people as rich as or richer than the corresponding individual. Now, to approach this systematically, we represent the relationships as a directed acyclic graph, or DAG. Each node represents a person, and a directed edge from one node to another indicates that the second person is wealthier than the first. The adjacency list representation of this graph allows us to traverse these relationships efficiently. Additionally, we initialize an array called answer to store the quietest person for each individual. This array is set to -1 initially and will later act as a memoization table to avoid redundant calculations during the traversal. The next step involves defining the depth-first search, or DFS, function. This function, DFS, node, determines the quietest person reachable from the given node, including the node itself. To make this efficient, if the quietest person for the current node has already been computed, we simply return the cached result from the answer array instead of recalculating it. Otherwise, we start by assuming the node itself is the quietest. Then, for each neighbor of the current node, we recursively compute the quietest person reachable. As we process these neighbors, we compare their quietness scores with the current quietest person and update the result accordingly. Once the DFS function is defined, we run it for every node in the graph to ensure that the quietest person for each group is computed. Finally, the completed answer array is returned as the result, containing the solution for the problem. This approach leverages some critical insights. First, by using a graph representation for the richer relationships, we can utilize graph traversal techniques like DFS to compute the solution efficiently. Second, the memoization array, answer, plays a crucial role in optimizing the algorithm. It ensures that each node is processed only once, significantly reducing redundant computations. Lastly, the recursive nature of DFS enables the quietness scores to propagate naturally through the graph. This ensures that the quietest person in a richer group is identified correctly as the algorithm traverses the relationships. The key data structures supporting this solution are the adjacency list, which efficiently stores and allows traversal of the richer relationships, and the memoization array, which caches intermediate results. Together, these structures enable the algorithm to handle the problem space efficiently both in terms of time and space. The algorithm's efficiency can be analyzed in terms of time and space complexity. Constructing the adjacency list from the input data takes O(m), where m is the number of richer relationships. Running DFS across all nodes takes O(n plus m), as each node and edge in the graph is processed at most once. Combining these, the total time complexity is O(n plus m). For space, the adjacency list requires O(n plus m), while the memoization array uses O(n). Additionally, the recursive stack for DFS may use up to O(n) space in the worst case, where the graph is a single long chain. Therefore, the total space complexity of the algorithm is also O(n plus m). These complexities make the solution highly efficient and scalable for large input sizes, ensuring that we can solve the problem within practical constraints. Here, we're implementing the solution using Python. First, we import the necessary modules, defaultdict for constructing the graph and deque for potential use in traversal. We define the loud and rich method inside the solution class, which takes two inputs, richer, a list of relationships indicating who is richer than whom, and quiet, an array where each index corresponds to a person's quietness level. The total number of people, n, is determined by the length of the quiet array. Next, we build an adjacency list to represent the richer relationships. For every pair, u, v, in the richer list, we add u to the list of neighbors for v in the graph. This means that v is richer than u, so we need to explore these relationships later. We also initialize a result array with -1 for all n individuals to store the quietest person associated with each node. Then, we define a helper function DFS to perform a depth-first search on the graph. Inside this function, we first check if the result for the current node has already been computed. If so, we simply return the cached value. Otherwise, we start by assuming that the quietest person for this node is the node itself. The next step involves exploring all the nodes that are richer than the current node, represented by its neighbors in the graph. For each neighbor, we recursively call the DFS function to find the quietest person in their subtree. If the quietness level of the candidate returned from the neighbor is less than the current quietest person, we update our quietest person to this candidate. Once we've identified the quietest person for the current node, we cache the result in the result array to avoid redundant computations during future visits. Finally, we return the quietest person for this node. After defining the DFS function, we iterate through all individuals, from 0 to n1, and call the DFS function for each one. This ensures that we compute the quietest person for every individual in the graph. Once the DFS is complete for all nodes, the result array contains the desired output, where each index maps to the quietest person associated with that individual. At the end, we return the result array as the solution. This approach ensures that we efficiently traverse the graph and leverage caching to reduce redundant computations. Here, we are implementing the problem using Java. To start, we import the necessary packages and define our solution class. The loud_rich method accepts two inputs, the richer array, which represents the richer relationships, and the quiet array, which provides the quietness level for each person. First, we determine the number of people, denoted by n, based on the length of the quiet array. Next, we create an adjacency list to represent the richer relationships as a graph. Each person is a node, and if someone is richer than another, we add a directed edge from the richer person to the poorer person. After initializing the graph, we iterate through the richer array to populate it with these relationships. Then, we define the result array, which will store the quietest person for each individual. Initially, we fill this array with -1, indicating that the values are not yet computed. Finally, we loop through each person and use a depth-first search to compute the quietest person for that individual, storing the results as we go. Once all computations are complete, we return the result array. The depth-first search, or DFS, is implemented in the private DFS method. This method takes the current node, the graph, the quiet array, and the result array as its parameters. The first step is to check if the result for the current node has already been computed. If so, we simply return the cached value to avoid redundant computation. If not, we initialize the quietest person variable to the current node, assuming it is the quietest by default. We then explore all the neighbors of the current node in the graph. For each neighbor, we recursively call the DFS method to find the quietest person in that subgraph. If the quietness level of the candidate returned by the recursive call is less than that of the current quietest person, we update quietest person to the candidate. After exploring all neighbors, we cache the result for the current node in the result array and return the quietest person. This approach ensures that each node is processed only once, making the algorithm efficient. In the loud_rich problem, we are tasked with finding the quietest person in a directed graph that represents richer relationships. Each person has an associated quiet value, and for every individual, the goal is to identify the quietest person who is either richer than or equal to them. To solve this problem, we use depth-first search, or DFS, along with memoization. This allows us to efficiently traverse the graph and calculate the results without redundant computations. For example, consider the input where the richer relationships are defined as 1, 0, 2, 1, 3, 1, and the quiet values are 3, 2, 5, 4. First, we initialize the graph based on the richer relationships, resulting in graph equals 0, 1, 0, 2, 1, 3, 1. Additionally, we set up a result array as -1, -1, -1, -1, indicating that the quietest person for each node has not yet been computed. Next, we perform a DFS traversal to compute the quietest person for each node. Starting with node equals 0, we observe that its result is uncomputed, so we initialize its quietest person as itself, quietest_person equals 0. Since node 0 has no neighbors in the graph, we directly cache the result as result 0 equals 0. Then, for node equals 1, we again see its result is uncomputed, so we begin by setting quietest_person equals 1. Here, node 1 has a neighbor, node 0, so we perform DFS 0, which returns 0. Comparing the quiet values, quiet 0 equals 3 and quiet 1 equals 2, we find that node 1 remains the quietest, and we cache result 1 equals 1. Similarly, for node equals 2, we initialize quietest_person equals 2. Its neighbor, node 1, leads us to call DFS 1, which returns 1. Comparing the quiet values, quiet 1 equals 2 and quiet 2 equals 5, we update the quietest person to node 1 and cache result 2 equals 1. Finally, for node equals 3, we start with quietest_person equals 3. Its neighbor, node 1, requires DFS 1, which again returns 1. Comparing quiet 1 equals 2 and quiet 3 equals 4, we determine node 1 is the quietest and cache result 3 equals 1. The final result is 0, 1, 1, 1. The output for this example is 0, 1, 1, 1, which means that the quietest person who is richer than or equal to node 0 is node 0 itself, for node 1 it is node 1, and for both nodes 2 and 3, the quietest person is node 1. Now, let's consider another example where the input contains no richer relationships. Here, richer equals, and quiet equals, 1, 0, 2. First, we initialize the graph, which remains empty since there are no relationships, resulting in graph equals. The result array is initialized as -1, -1, -1. Without any neighbors for any node, we proceed with the DFS traversal. For node equals 0, since it has no neighbors, we directly cache result 0 equals 0. Similarly, for node equals 1, we cache result 1 equals 1, and for node equals 2, we cache result 2 equals 2. Each node is its own quietest person. In this scenario, the final result becomes 0, 1, 2. The output indicates that for node 0, the quietest person is node 0, for node 1, it is node 1, and for node 2, it is node 2. This makes sense, as there are no richer relationships in the graph, so each person is their own quietest. Now, let's analyze another example with a more complex set of relationships. Here, richer equals 0, 1, 1, 2, 2, 3, 3, 4, and quiet equals 5, 4, 3, 2, 1. The graph is constructed as graph equals 1, 0, 2, 1, 3, 2, 4, 3. The result array is initialized as -1, -1, -1, -1, -1. Starting with node equals 0, we see it has no neighbors, so we cache result 0 equals 0. For node equals 1, we observe it has a neighbor, node 0, so we call DFS 0, which returns 0. Comparing the quiet values quiet 0 equals 5 and quiet 1 equals 4, we update the quietest person to node 1 and cache result 1 equals 1. For node equals 2, its neighbor, node 1, requires DFS 1, which returns 1. Comparing quiet 1 equals 4 and quiet 2 equals 3, we update the quietest person to node 2 and cache result 2 equals 2. For node equals 3, we call DFS 2, which returns 2. Comparing quiet 2 equals 3 and quiet 3 equals 2, we update the quietest person to node 3 and cache result 3 equals 3. Finally, for node equals 4, its neighbor node 3 leads to DFS 3, which returns 3. Comparing quiet 3 equals 2 and quiet 4 equals 1, we update the quietest person to node 4 and cache result 4 equals 4. The final result is 0, 1, 2, 3, 4, where each node finds the quietest person in its richer path. To analyze the time complexity of the solution, we need to break it down into 3 main steps. First, the graph construction step processes the richer list, which contains pairs of relationships. Each pair is inserted into the adjacency list, and since we perform this operation for all pairs, the time complexity for this step is O(E). Next, we have the DFS traversal. Here, the DFS function is called once for each node, and the traversal explores all of the neighbors of a node. The key point is that memoization ensures each node is processed only once, so every edge in the graph is visited at most once. This means the total time spent on DFS is proportional to the number of edges, which is also O(E). Finally, constructing the result array requires storing the quietest person for each of the n nodes, which takes O(n) time. By summing these steps, we can start to see how the time complexity forms. When we combine all the steps, graph construction, DFS traversal, and result construction, the overall time complexity becomes O(E) plus n, where E is the number of edges and n is the number of nodes. Now, let's look at the space complexity. First, the adjacency list representation of the graph requires O(E) space, as each edge creates an entry in the list. Second, the result array, which stores the quietest person for each node, takes O(n) space since there are n nodes. Finally, the recursive DFS calls can use additional stack space proportional to the depth of recursion. In the worst case, this depth equals the number of nodes, requiring O(n) space. Together, these components contribute to the overall space complexity. Adding up the space requirements, the adjacency list, the result array, and the DFS call stack, the total space complexity is O(E) plus n. Now let's compare this solution to a brute force approach. In a naive method, we would compare every person with every other person to find the quietest richer individual for each node, resulting in O(n) squared comparisons. This approach becomes impractical for larger inputs. The optimized solution, however, leverages the graph structure and uses memoization to avoid redundant computations. By traversing the graph efficiently and caching results, we reduce the complexity to O, E plus N, which is particularly advantageous for sparse graphs where E is much smaller than N-2. Let's examine the solution under different scenarios. In the best case, when the graph has no edges, the adjacency list is empty, and the DFS function processes only the nodes, making the time complexity O, N. For an average case, in a sparse graph where the number of edges is proportional to the number of nodes, we have E equals O, N, and the time complexity simplifies to O, N. In the worst case, with a dense graph where E approaches O, N squared, the time complexity becomes O, N squared. To validate this mathematically, the graph construction step is O, E, the DFS traversal processes each node and edge exactly once for O, N plus E, and the result array processing adds O, N. Summing these, we get O, E plus N. For dense graphs with E equals O, N squared, the total becomes O, N squared, while for sparse graphs with E equals O, N, the total reduces to O, N. In graph-based problems like Loud and Rich, it's crucial to understand the directed nature of the graph. Relationships such as A is richer than B imply a one-way dependency, meaning the information flows from A to B but not the other way around. Treating the graph as undirected can lead to traversal errors, where you might incorrectly assume relationships are mutual. Another common mistake is recomputing results for overlapping subproblems. For instance, if you're determining the quietest person in a group, recalculating the result for each node without caching can lead to highly inefficient runtimes, sometimes exponential in complexity. This is why memoization is such a powerful strategy. Lastly, edge cases shouldn't be overlooked. Scenarios like an empty graph or duplicate values in the quiet list are often included in test cases to catch unprepared solutions. These may seem minor, but failing to handle them can lead to incorrect outputs during critical evaluations. Topological sorting is another important consideration when dealing with directed acyclic graphs. Processing nodes out of order can prevent dependencies from being resolved properly, leading to flawed results. For example, if a node depends on another that's processed too late, your solution may fail to account for the correct relationships. Likewise, inefficient graph traversal is another pitfall. Using unoptimized DFS or BFS, such as failing to track visited nodes or using a less efficient representation like adjacency matrices, can significantly increase time complexity. This becomes especially problematic when the graph is large, as poorly optimized traversal methods can lead to performance issues that fail scalability constraints. It's essential to ensure your solution is both logically correct and computationally efficient. When preparing for interviews, understanding the nuances of graph representation is key. You should always clarify whether the graph is represented as an adjacency list, a matrix, or an edge list. Adjacency lists are typically more efficient for larger graphs due to their compact representation. Topological sorting is another critical pattern to master, especially in DAG problems. Both Kahn's algorithm and DFS-based approaches are useful, and being able to explain how nodes are processed in dependency order is a valuable skill. Similarly, problems involving overlapping subproblems often benefit from memoization to reduce redundant calculations. It's also important to explicitly discuss edge cases during interviews. These include scenarios like empty graphs, single-node graphs, or even cyclic dependencies, depending on the problem's constraints. Familiarity with related problems, such as LeetCode 802, 310, and 207, can provide additional insights into solving graph-based challenges. Each of these problems highlights key concepts like finding safe states, central nodes, or applying topological sorting in creative ways. There are multiple approaches to solving graph problems, each with its own trade-offs. Using DFS with memoization is a popular choice for its simplicity. By traversing the graph recursively and caching results for each node, you ensure each node is processed only once, achieving a runtime of O, V plus E. However, this method may require significant stack space for recursive calls in deeply nested graphs. Alternatively, BFS with topological sort, such as Kahn's algorithm, offers an iterative solution. This approach avoids recursion while efficiently processing nodes in dependency order, although it requires managing in-degree counts, which can be less intuitive for beginners. Finally, union find, or disjoint set union, is particularly useful for problems involving connected components or propagating properties like the quietest person in a group. While powerful, it's less suited for dependency-based problems and may require additional explanation to justify its use. Each method has its strengths and weaknesses, and choosing the right approach depends on the specific problem constraints and requirements. Great job! To summarize, we tackled the loud and rich problem by modeling it as a graph and using DFS to find the quietest person for each individual efficiently. This problem highlights the importance of leveraging graph-based algorithms to handle constraints. Thank you for watching, and don't forget to like and subscribe for more engaging problem walkthroughs. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!